ladies and gentlemen, for all of you who haven't signed the breakout rooms, you may choose freely from 3 breakout rooms that we'll provide, and you may enter any room that you are interested in. Thank you.
To all participants, the first room will be Yuli Rahmawati, PhD, from the State University of Jakarta, Indonesia, and will be led by Professor Solistio Saputro as a moderator. For the second room, the invited speaker will be Dr. Muhammad Mashkuri from Universitas 11 Maret, Indonesia, and will be led by Dr. Endang Susilawati as a moderator. And for the third room, the invited speaker will be Dr. Maria Ulfa from Universitas 11 Maret, Indonesia, and will be led by Dr. Elvi Susanti as a moderator.
Welcome to all of the participants to the main room. And also thank you for all of our invited speakers who has given interesting presentation to all of us. The next agenda is parallel session. For all of the participants, will be divided into 6 breakout rooms. The committee already provides 6 breakout rooms, and please choose a breakout room according to what is stated in the book of program. Thank you.
Hi, Chris.
Morning, Mohammed. Good morning, everybody.
Good morning, Chris. So now we are still having another session. It's the parallel sessions. So we are waiting for the participants to come back to the main room. Is it okay
That's fine.
with you?
Yeah.
Maybe because like in our schedule, we will start our session at 3:15, right? And I mean 8:15 in 9 in your time, in UK time. So do you want to try your slide or anything you want to try, or?
I can try and share now as long as it doesn't screw up everything else.
No, I have already set you up as the co-host, so you can share your screen.
Okay, let me just get things set up then.
Oh yeah, Chris, here we have our head of study program. There is Dr. Sri Mulyani.
Good morning.
He's still inside and mute.
Yeah, that's pretty universal, I think.
Yeah.
Good morning, Mr. Rainer.
Good morning. Nice to meet you. Thank you for the opportunity to speak today.
We also thank you for for you to be our keynote speaker, Chris.
That's my pleasure. Yeah. So Mohammed, I've tried to share my screen and it's coming up with advanced sharing options.
Wait a minute.
Can you see it at all or not?
No. Wait a minute. I think because the operator has already has been sharing this slide, so you couldn't share your screen. Let me check to the operators to stop the screen share screen, and then you can share your slide.
Okay.
Yeah, operator has already entered the share screen. Could you please start your share screen, please?
Yeah. Hang on. Can you see that?
Yeah, it's clear. Yeah, totally fine. Yeah, that's all right, Chris. Thank you very much.
Can I just try something else? Just 1 second. Let me
Sure,
just try. I have multiple screens and it will get a little complicated.
Sure. Yeah, you can try it now.
Yeah, that's going to be the easiest, I think, actually. So you should be able to see that now, I guess. Yeah.
Yeah, we can see that.
I'm just going to move my camera around because it's done on my other screen and it looks like I'm not looking at people.
No problem.
There we go. Okay, very good. All right. I'll just stop sharing that then.
Yes.
And you can hear me okay? Yeah.
Yeah, your voice is clear. Can you hear my voice clearly, please? Or
I can hear a little quiet, but I think that's a problem with my speaker. I've just turned you up a little bit. So.
Yeah, as we discussed yesterday, you will have 1.5 hours. But
I don't think I'll take all 1.5 hours, but I'm quite happy to talk for as long as people have questions, I guess.
Yeah, sure. Yeah. I mean, the maximum for the presentation is 1 hour and then 15 minutes for the question and answer. I think that's all. You can if you said yesterday that you are going to present also the Caracol, or today just C capture, Chris?
No, just C capture in the end. I mean, so it will be 40 to 50 minutes, something like that. But as we said yesterday, Mohammed, I will be speaking very slowly
And not very slowly. As long
So
as
I
we
don't
can
know how
understand what you're saying, that's fine.
Okay, I'm just going to get a glass of water, Mohammed. I think we're
Sure,
okay.
sure. Yeah,
haven't
yeah,
we?
yeah.
We've got a
We'll
few
come
minutes,
back in
yeah.
a few minutes. No worries, no worries. Thank you
Yeah,
very much,
okay,
Chris.
all right.
See ya.
Cheers.
Hi, Chris. It seems that the parallel session hasn't ended yet. Would it be possible for 10 minutes?
Yeah.
Yeah.
No, that's fine. I have
Yeah,
something at 11, Mohammed. That's the main thing. So, but we have another 10 minutes. That's absolutely fine.
Yeah. Sorry about that, Chris.
No, that's okay.
Welcome back, ladies and gentlemen, from the parallel room to the main room of International Conference on Chemistry and Chemistry Education, Surakarta, 19 August 2022. Ladies and gentlemen, we are now continuing our meeting to the next agenda, that is to listen to the presentation from our third keynote speaker, Professor Chris Rainer from University of Leeds, United Kingdom, led by Dr. Muhammad Hisbul Waton from Universitas 11 Maret as a moderator. Before we start the presentation session, I would like to introduce our moderator, Dr. Muhammad Hisbul Waton. He is a lecturer from 11 Maret Chemistry Education Program, and he is an expertise in natural chemistry. Ladies and gentlemen, please welcome Professor Rainer and Dr. Waton.
Thank you very much, Satria, for the opportunity. Good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh. In this session, we will be having our keynote speaker, Professor Chris Rainer. He is an expert in organic chemistry. His main research is about the chemistry of carbon dioxide, particularly use of high pressure carbon dioxide in chemical processes and reaction of carbon dioxide for removal from gas streams for application in capture and storage and biogas upgrading. For the carbon dioxide field, he has a spin out a company called C Capture, and then we will hear more about C Capture later on in his presentation. Another area of his research is extraction and utilization of natural products in consumer products and in novel medicines. In this field, he also has a spin-out company called Caracol. Without any further ado, please, Professor Chris Rainer, to give a presentation regarding the carbon capture storage. Time is yours.
Okay, thank you, Mohammed. Let me just share my screen. Get my pointer up. Okay, so good afternoon, everyone. First of all, thank you to Mohammed and Dr. Sri Mulyani and all the conference organizers for the opportunity to speak to you this afternoon. It is indeed this morning in Leeds, so it's about 9 o'clock, 9:30 in the morning, and I'm very grateful that you didn't arrange for this conference to be in the morning your time, otherwise I would be up in the middle of the night. So I really appreciate that and the opportunity to speak now. So I appreciate for most of you that English won't be your first language, so I will try and talk reasonably slowly, reasonably clearly, probably a little more slowly and clearly than I usually do. So I hope you'll be able to understand what I say, and I do apologize for my English accent in the right at the beginning, but I will do my best for you. So as Mohammed said, this is about a research project that we started probably about 15 years ago. It originated from one PhD student, actually from India, and she was working on trying to develop new chemistry around the chemistry of CO2, of carbon dioxide, and thinking about whether there are better ways to capture it than the existing technology, which is based on amine chemistry. And throughout the talk, I'll give you some examples of what people currently do or have done historically, and then I will tell you about what we've been doing in Leeds, and in particular the chemistry that we've been using at C Capture and some of the developments there where we are starting to scale up the chemistry so that it can actually work on a very large scale, which is the sort of thing we really need to do if we're going to combat climate change. So just a little bit of history. I'm sure some of you will be familiar with this sort of thing, but in 2015, we had the Paris Agreement, which was a legally binding agreement where nations would come together to try to limit climate change. And in particular, we would try to reduce global warming to certainly 2 degrees and preferably below 2 degrees. And it turns out that 1.5 degrees now is essentially the target there. So you can see here, this is the Paris Agreement treaty. It was actually a major achievement when it was signed up. And since then, a lot of people have been working towards 1.5 degrees. One of the key things is for 1.5 degrees, even if we are able to limit things to 1.5 degrees, there are still going to be some major consequences for us in terms of the impacts of climate change, in terms of things like flooding, fires around the world, and things like that. And of course, for many of us, we're already seeing examples of that. You only have to watch the news and you will see examples of wildfires in sort of Western USA, in Australia. We have many floods around the world, all sorts of things, and they're getting worse, and we're nowhere near 1.5 degrees yet. So things are pretty urgent now, and we need to be acting on this. So in the UK, we have something that we call the Committee on Climate Change, and they have a strategy for achieving net zero, which they are trying to get the government to adopt, and things are progressing pretty well, but still, pretty much everybody around the world is moving too slowly, and we all need to accelerate what we're doing towards net zero, towards reducing CO2 emissions. So just to put things into context a little bit, so the current atmospheric concentration of CO2 in the atmosphere is around 412 parts per million. It's not very much, but of course the problem is it's going up continuously. So pre-industrial levels was around 280 parts per million, and so it's gone up by probably 50% over the last 100 years or so. So it is increasing quite significantly. And the current levels of CO2 emissions are around 30 gigatons per annum. Although total greenhouse gases, which include things like methane emissions and land use changes, double this essentially to around sort of 50 to 60 gigatons of CO2 per annum, or gigatons of CO2 equivalent per annum. And for those of you perhaps not so familiar with the term gigaton, a gigaton is around 1,000 million tons. You can see down here. So it's a lot of CO2, and we have been pumping this out for many years, and we continue to do that, and we need to reduce that essentially down to what we call net zero. It'll be impossible to actually stop emissions totally. So what we have to do is also find ways to achieve negative emissions. So effectively ways of taking CO2 out of the atmosphere and not just stopping CO2 being emitted into the atmosphere. So I dug out a few numbers, particularly I want to see what the position was with Indonesia. And these are some CO2 emissions. They're very approximate. They are from the World Bank, so that shouldn't be too bad, but it does depend very much on what kinds of things you take into account when you calculate these numbers. But for China, you can see that's the major emitter, 10.7 gigatons of CO2 per annum. That's around 7.6 tons per person. In the USA, 4.8 gigatons, so roughly half that of China, but you can see it's roughly the double the amount per person. In the UK, we're actually doing quite well, 5.2 tons per person. Sorry about the spelling mistake there. But we are a relatively small player. But the problem is almost everybody is a small player. It's when everything comes together that actually things really have to happen. And Indonesia is around 620 million tons per annum, but you can see a lot less per person than many of the other countries there. So we all need to do our bit. We all need to come together. And the UK government itself is committed to net zero emissions by 2050, and that's a legally binding target. So the government is going to be held to that. But with everywhere around the world, one of the problems is holding the current governments to account for what might happen in 25 years' time, for example. So there are real challenges there in getting government to adopt these these targets. And that occurs around the world. So, certainly in the UK, we're pushing a lot for this sort of thing. And I would hope everybody else around the world is doing similarly. And certainly in the USA, things have changed a lot over the last year or two with the IRA Act that Joe Biden recently introduced. That's very, very significant. And China have also reduced their emissions quite significantly, or at least they're very close to working on that. And of course, one of the problems China has is it manufactures most of the things for the rest of the world. So although they have a lot of emissions there, of course, they do manufacture a lot of things for everybody around the world to consume. So they have a particular challenge. So let's just focus a little bit on net zero and how do we get there. And of course, the key thing is we need to fundamentally reduce global emissions wherever we possibly can. It really is an unprecedented transition in how we produce, transport, and use energy. The Industrial Revolution has basically increased our CO2 emissions, and now we need to very quickly get it back the other way, and that's going to be quite difficult. So renewables, there's something just come up on my screen. I'm not sure what it is, Mohammed. It says breakout rooms in progress. I don't know whether you can get rid of that. But
yeah, it's been removed.
I've got rid of it. There you go. Hopefully I haven't destroyed somebody else's breakout room, but never mind. So renewables will play a huge role in this. So renewables, sort of solar and wind power, maybe tidal power, lots of other sources of energy will play a huge role in this. But what I'm going to focus on today is what we call carbon capture and storage, or CCS. It's a key technology for decarbonisation of the UK and also around the world. And particularly this applies to any heavy industry where you've got a very large point source emitter of CO2. So it could be a power station, it could be an iron and steel works, it could be a cement works, it could be glass ceramics. So it's required to reduce emissions from sectors which are really hard to decarbonise. So cement, iron and steel, glass ceramics. Waste to energy, so burning energy and getting some energy back from that waste rather than just burying it. Chemical manufacture, oil refineries, and even hydrogen production. So there's lots of different ways we can impact on CO2 emissions using carbon capture and storage. And as I mentioned, you can actually reduce CO2 emissions, but you can only get so far. If you're manufacturing stuff, there's always going to be some residual CO2 emissions that you just can't get rid of. And for that reason, we need things that we refer to as negative emissions technologies. And I'll talk about one of those today, which is bioenergy with CCS, or BECCS. And basically this represents a method of taking CO2 out of the atmosphere and putting it underground, so burying it. It's essentially the reverse of what we've been doing for the last 100 years or so, where we've been digging fossil fuels up, burning them, CO2 into the atmosphere. Can we do the opposite? And that's really what we want with the negative emissions technologies. And most pathways that limit global warming to 1.5 degrees centigrade rely on very large scale deployment of BECCS alongside things like afforestation, for example, other ways of actually sequestering CO2. Okay, so let's get down to some chemistry and talk about CO2 separation. So this is a very common slide. It applies to a lot of different types of chemistries that you can use to separate CO2 from other gases. So what you typically have is a feed gas stream. And so that can be from a power station, it can be from some industrial process. And you apply a process to that, and what you get is two streams. One is carbon dioxide, and that's what we're going to be focusing on. And the other stream basically is everything else. So essentially you're separating the carbon dioxide from everything else. And usually, for example, if it's a flue gas from a power station, it will be oxygen and nitrogen, and then some low-level impurities of other things that usually arise from the fuel. So we're separating CO2 from everything else. So how do we do that in practice? So it relies on CO2 reacting selectively and reversibly with a solvent, where other gases do not, and essentially they pass straight through the solvent. So Once you've captured your CO2, what can you do with it? Well, typically what is happening in the UK and also around Europe and the US is it's going underground. Essentially, it's going back where it originally came from. And there are various different places where you can sequester the CO2. So it could be in a saline formation, for example, big hole in the ground that's there from salt water, basically. You can inject it into deep unminable coal seams or other coal-based processes. You can use it in a process called enhanced oil recovery, and this is quite controversial. And certainly in the longer term, once we stop digging up fossil fuels out of the ground, this won't be used anymore. But what you can do is pump CO2 down into the ground to where there is some oil, and the CO2 actually makes the oil much more mobile, so it will come out. And so you can isolate your fossil fuels through that. Of course, if we're going to stop extracting fossil fuels, this will become less important. But at the moment, it has become quite important because what it's allowed us to do is develop the technology for CO2 capture on the kind of scale that is required. So to demonstrate it, because at the moment, nobody's willing to pay for CO2 capture and storage. So if you can find a method of generating some income when using carbon capture and storage, then that really helps in the economics to actually demonstrate the technology. And that's what's happened with enhanced oil recovery. And in the UK, we're going to tend to put things in depleted oil and gas reservoirs. So in the North Sea, just off the east coast of the UK, we have historically had large deposits of natural gas and oil. And we've taken essentially a lot of that natural gas and oil out, and we have holes in the ground. And so we can essentially put the CO2 back there offshore, which is probably the main thing for the UK. It varies very much on location. So the US, for example, is very much into onshore storage, but in the UK, we're more focused on offshore storage. And then finally, one that is kind of interesting, very challenging is utilization. So can you do something with the CO2? Can you do some chemical process with it, for example? Can you use it in some sort of other industrial process? And that really is a real challenge. One of the reasons we have a lot of CO2 around is because it's the bottom of the energy well. And so to actually do anything with CO2, you've got to put some energy in. And so if you're doing it on the kind of scale that you would need to actually have some sort of impact on climate change, then you need a lot of energy to use that CO2. So utilization is potentially important, but it is a real challenge. Okay, so some chemistry now on CO2. And this is basically what happens when you mix CO2 with water. So we refer to CO2 as an acid gas. So it does have acidic properties when it dissolves in water. But of course, when you think about an acid, CO2 hasn't got any hydrogens. It hasn't got any protons. So of course, it can't be an acid itself. And of course, it's what happens when the CO2 reacts with water that is important here. So you can actually get a reasonable amount of CO2 dissolved into water. You can get probably about 90 mils equivalent gaseous CO2 dissolved in about 100 mils of water. So you can get a reasonable amount in there, but remember, it's gaseous kind of density, so it's not huge amounts. So you can get CO2 dissolved in water. And when CO2 does dissolve in water, you get like a carbonic acid here. Okay. So carbonic acid is probably what everybody thinks you form when you dissolve CO2 in water. But if you look at the equilibrium constants here, less than 1%, probably less than 0.2% of the CO2 that's dissolved in water is present as carbonic acid. Most of it is just dissolved CO2. There is some carbonic acid in there, but only a relatively small amount. And you'll see the pKa of carbonic acid is around 3.6. But of course, because there's only a relatively small amount of it in there, the overall pKa of CO2 in water is actually significantly higher. And that's at this bottom equilibrium here. So the effective pKa of CO2 in water is around 6.3. So although carbonic acid is 3.6, because there's relatively small amounts of it in there compared with all the other CO2, the actual observed pKa is actually significantly higher than that of just carbonic acid. So there's lots of interesting aspects to CO2 when you dissolve it in water. It's not straightforward chemistry. It's certainly not straightforward acid-base chemistry. You know, if you're mixing sodium hydroxide with hydrochloric acid, that's relatively easy and predictable. For CO2, it's a little bit more complicated. And that can have very important implications, as you will see. And for CO2 capture, pKa is incredibly important. Okay? And what I've listed here are some typical reagents that are used for CO2 capture. I'll spend some time talking about this species here. This is monoethanolamine, or at least protonated monoethanolamine. The pKa of this hydrogen here is around 9.5. N-methyl diethanolamine, pKa is 8.52. Piperazine, 9.8. Ammonia, 9.2. Interesting here, phenol. We've done some sort of work with phenol, where this is, of course, is a nitrogen-free system. And one of the things we've focused on as a research group and with Sea Capture is trying to develop capture agents that don't have nitrogen in them. There are some inherent problems with nitrogen, particularly if you're trying to capture CO2 in a flue gas, in that it very quickly oxidizes and degrades with the residual oxygen that's typically in a flue gas. And so there are some major issues there. Whereas if you have something like a phenol, there are no nitrogens, it's much less prone to oxidation, and there are other functional groups where you can do that as well. And so any amine or other species with a pKa greater than CO2 in water, and the pKa is 6.3, so anything with a pKa greater than 6.3 can potentially capture CO2 via an acid-base process. So MEA is one I'm going to spend some time talking about. So that is monoethanolamine, where of course you don't have this hydrogen here, but that is actually formed as part of the capture process. So let's look at what happens with MEA, or monoethanolamine. And this is sort of representative of how things have been done historically. So CO2 reacts very quickly with primary and secondary amines to form carbamates. So here's your MEA. It reacts with CO2, and your CO2 ends up forming this carbamate here as an ammonium carbamate. Okay, and you can see in this particular case, you have one molecule of CO2 for 2 molecules of MEA. So it's a relatively inefficient process. You're only ever going to get 50% loading compared to the MEA the amount of MEA that you're using. So 2 equivalents of the amine required there. There's an alternative pathway as well, though, that requires water, where CO2 is absorbed into an aqueous amine solutions by formation of bicarbonate, or potentially carbonate, but carbonate is usually very low levels because it's just too high pKa. And for this, 1 equivalent of base is required. So what you've got here is your amine again, but now CO2 with water, you form the ammonium bicarbonate. And so that's where the CO2 ends up there. And the nice thing here is, of course, it's a 1-to-1 mixture ratio of the CO2 to the MEA. So that looks great, but the problem here is the absorption rate is actually very slow. So it's actually quite challenging to do bicarbonate-based processes. It can be done, but it's quite challenging. And what you normally see is a combination of these two, as you'll see in a second. So bicarbonate, it's less stable than carbamate, and that's better stoichiometry. Bicarbonate production gives more efficient, less energy-intensive regeneration, but it's often slower. And what we've done over the last 10, 15 years or so is look at carbamate bicarbonate speciation on the laboratory scale, and that's really allowed us to understand some of the key factors that are required when you're thinking about large-scale performance. And so when you just take MEA, monoethanolamine, react it with CO2, aqueous CO2, this is what you form, and actually essentially a mixture of the carbamate, bicarbonate, and the ammonium salt. And that changes, and the ratio here changes as the reaction proceeds. And so you can actually follow it by NMR. So here's the NMR when you have a 5 molar monoethanolamine, and you're bubbling CO2 through, and as you bubble through, the species change. And so what the blue dots, sorry, blue squares are monoethanolamine, and the red dots are carbamate. And you can see at the beginning you have predominantly monoethanolamine, and then as you increase the amount of CO2 present, the carbamate starts to increase, like so, and you get the ammonium carbamate at the bottom there. To actually see bicarbonate and things like that, of course, you can't see that on a proton NMR. You can do it on carbon-13, but it's a bit more challenging to do that quantitatively. But you can see it and do comparable things. But this shows you how, over a period of time, you can see how the species change as loading increases. And it's quite interesting how it does change. So remember, the carbamate formation is fast, bicarbonate is slow. And so for 5 molar MEA, for example, if we're looking at the formation of bicarbonate or the carbamate here, at the beginning, when you've got, essentially you're just introducing CO2, all the capture is via this species here, which is the carbamate. It's only when you get to roughly 50% concentration, so 2.5 molar, that the bicarbonate now starts to kick in. And that's because this is the slow process. It will only start to compete once you've exhausted the fast process, the carbamate formation. So you can get quite a complicated mixture here, and it's not straightforward to actually do all of this. And of course, the key thing about all of this is reversible chemistry. You need to capture the CO2, but then regenerate your absorbent and give you a CO2 stream that you can then go and store underground. And typically you will do this with heat. So if you take this mixture that you get when you just treat MEA with CO2 and heat it up, what happens is you regenerate the MEA and the water, and the CO2 comes off as a gas, and then you can actually compress that and store it underground. And you need to heat up to do this, and typically about 120 degrees, maybe hotter. And so, of course, you use a lot of energy by doing that. And that's the main energy cost of this process. You have to heat it up and then cool it down to recapture and heat it up again. So it's over a prolonged heating and cooling cycle. So this cost is primarily due to the stability of the carbon capture products and the heat capacity of the water and the steam losses. So those are all the kinds of things you have to consider when you're working out the energetics and the economics of this process. Monoethanolamine-based capture systems will require about 20 to 30% of the output of a typical coal-fired power station. So you can see that's quite a significant parasitic load, we call it, on the power station. And carbamates are significantly more thermostable than bicarbonates. So when you heat these up, for example, the bicarbonate degrades first, and then the carbamate. And so any process that involves a carbamate usually is more energy intensive. If you can have a process that's exclusively bicarbonate, then usually the energetics of that are significantly reduced. So how is this done in practice? Well, I'll show you some pictures later on, but basically what you have is an absorber column, and this absorber column is essentially at about 30 or 40 degrees centigrade, so slightly warm, but effectively a low temperature. And what you have is your solvent that actually is coming down, rains down the absorber column, and you blow your gas in from the bottom. So the gas, your flue gas, which has got the CO2 in it, comes in at the bottom and travels up the absorber. And during that process, it comes into contact with, say, your monoethanolamine, whatever, and reacts to form your carbamates or bicarbonate, and then travels down. The other gases that are present in your flue gas, so the nitrogen, for example, or the oxygen, they don't react with the MEA, and so they keep going up, and eventually they'll come out the top. And so at the bottom of the absorber, what you have is your MEA loaded with CO2, or your absorbent loaded with CO2. That CO2-rich solvent is then transferred via a heat exchanger into a desorber, and this is typically at around 120 degrees centigrade. At those temperatures, what happens is you get the reverse reaction, so the CO2 comes off, and so as a gas, it can come out the top, and your amine comes down, and by the time it gets to the bottom, essentially the vast majority of the CO2 comes off, and you're left with your regenerated amine that you can actually recycle and reuse. So you have that recycling and reuse is very, very important. And one of the key things is over time, amines like monoethanolamine do degrade. And we spent a lot of time talking about this, looking at this in my research group. It does degrade, and that greatly impacts on the efficiency of the process. You imagine these are very large columns. I'll show you some pictures later on. The amount of MEA you use is very, very large. And so significant degradation is a major issue. Okay, and so when the CO2 comes off the top here, what you would do with it is compress it, usually to about 100 bar, and then it can be transported and put underground. Of course, if you're lucky, you can do some utilization with it or some other things. So there are some inherent problems using amines, and we spent a lot of time trying to understand all of these. So, for example, many amines are highly corrosive to steel, particularly when they're concentrated, and so you need quite costly corrosion-resistant materials. They are prone to degradation, necessitating regular replacement of the capture solvent, so you're continuously topping it up because it's degrading. Imagine you've got an alcohol in there, an amine functional group, a primary amine, that can react with oxygen over a period of time where you're heating it up, and that means that your amines do degrade. Amines like MEA are relatively volatile, leading to significant environmental release of often toxic compounds, not always, but there can be some significant toxic compounds, particularly things like nitrosamines, that can be formed with certain amines, and you have to be really careful there. And energetic performance for amines is still modest, and improvements are incremental where people are changing from one amine to another, or actually using mixtures or blends of amines these days. Very, very popular approach. And indeed, amines have been around for many, many years. So this is the original patent for using amines, which was originally in the 1930s. So 90 years ago. It's very, very old technology. And this was the basis of our research project. Could we do something fundamentally different chemistry that would allow us to actually capture CO2 effectively? So solvent-based CO2 separation has been around since the 1930s. It was originally developed for natural gas sweetening. So natural gas in the ground, when it occurs naturally and you get it out, it has a lot of carbon dioxide in it and hydrogen sulfide as well. And you can use these amine type processes to remove the carbon dioxide and the hydrogen sulfide to give you a pure natural gas that you can then use in your homes, for example, for home heating or cooking or other applications. It was originally developed for natural gas sweetening, but the problem is there, when you use it for natural gas sweetening, you don't have the other issues that you have with carbon capture and storage. So for example, the CO2 content is actually quite a bit lower for many CCS applications. There are lots of impurities that you get from various different flue gas sources. There is quite a lot of oxygen still, and even though in a flue gas from a power station you think you've burnt everything, so there shouldn't be very much oxygen there, there can be quite a lot of oxygen still left in there, sort of at least 8 to 10%, if not higher. And then finally, of course, scale. If we're doing this to combat climate change, we have to do it on a huge scale, and probably a larger scale than natural gas sweetening has ever been carried out. So major issues there. So there are challenges associated with the amine-based system, and this is what we wanted to overcome with our research project. And so on the basis of some research we did, we established a company called CCapture in 2009, so 13 years now, as a spin out. And the goal really was to create the most energy efficient CO2 capture solutions through chemistry and engineering innovation. And it is chemists and engineers here working together that is vital. So there's lots of companies working where they are very much engineering focused and don't really do much on the chemistry side of things. Whereas we were quite different in that we wanted the chemists and the engineers to work together very, very closely so we can change the chemistry and also change the engineering if we need to. That chemistry engineering interface is something I've been working at for a long, long time, and it is very, very important. And of course, the key thing here is to create solutions which are viable on a large scale. There's no point in doing this if it's some very, very expensive material that you can make a gram of you need to be able to make tons and tons of the material to capture the CO2 relatively easily. And, you know, I say at the bottom there to play a role in saving the planet. When we first started this, that was never really on the cards. We never in our wildest dreams thought we might get to that sort of stage. But actually the technology that we now have really is outstanding technology. Probably, even though I may say so myself, I think one of the best in the world. And so we have a wonderful team, a couple of our employees here, Rose and Fatima. So Rose is one of our key engineers. Rose is one of our key chemists, and Fatima is one of our key engineers. And they're actually on site at Drax, a big power station in the UK. And I'll tell you a bit more about the work we're doing there in a short while. So, amine free solvents, how can we do this? Okay, so we looked at a very wide range of different capture agents. And remember, we talked a little bit about pKa earlier on, how you need the pKa of the conjugate acid to be higher than the pKa of CO2. And one class we looked at, and this is a little bit counterintuitive to start off with, is carboxylic acids. And if you think about carboxylic acids, the pKa of, say, acetic acid, for example, here in water, it's about 4.76. So that is lower than the pKa of CO2 in water. And so effectively, it won't act as a carbon capture solvent. Okay, the equilibrium just doesn't work, and it won't capture the CO2. However, pKa is a curious thing, and many people think pKa is relatively straightforward, but it's not. It's actually very complicated. And in particular, it varies very much depending on the environment in which the species is dissolved. And so if we remember these equilibria here, when you look at the pKa of something like acetic acid in different solvents, the pKa changes dramatically. And it's all, of course, to do with the stability of the carboxylate anion versus the proton, how the solvent solvates those and stabilizes those species. Water, of course, is very good at that, but a lot of other solvents are not. And if that's the case, then you very much disfavor this dissociation, and so the pKa goes up. And you can see, remember, each pKa unit is effectively an order of magnitude, so you can go from essentially 5 in water to 10 in methanol and ethanol, GMSO, and you can see when you get down to acetonitrile, the pKa is around 20, 23. And that's a huge change in the acidity there of the carboxylic acid. And so what we've been doing is utilizing that change in a rather specific way to develop carboxylates that can capture CO2. And so this is some work by James Wheatley, a PhD student in my group from a little while ago, who now works for Sea Capture. And this is looking simply at the pKa and how pKa changes depending on how the solvent, in this case DMSO, and water changes. So when you've got 100% water, the pKa is around 4.7, as we've seen. But as you gradually increase the amount of DMSO, you can see when you get to these levels here, where you've got 95% levels of DMSO, the pKa goes much higher. The important thing, though, is relative pKa. So you've got to also think about what happens to the pKa of CO2 in water under similar changes. So what happens to carbonic acid or actually CO2 in water? And although it's higher, so in water, of course, it's 6.3, what we've seen. But as you change the solvent, so you increase the amount of DMSO, you can see by the time you get up to these high organic ratios, the pKa's of the CO2 and the carboxylate now are quite matched. Okay, so there's very delicate balance. And so now you do see significant capture. And it's very finely balanced, much more finely balanced, for example, than CO2 and monomethanolamine, where it's very much just a one-way process. Here you can actually tweak the pKa's, you can tweak the balance to actually optimize your capture process. Now, I will say that the components that we use are confidential. I wouldn't be showing you this if we use DMSO and acetic acid, but it's very similar principles that we use within Sea Capture. And so there is our solvent. That's a bottle of it. This is Doug Barnes. So Mohammed will know Douglas very well. Doug did his PhD with me. He's now the head of chemistry at Sea Capture, and Rose, again, they're one of our other chemists, and they're sort of looking longingly at our solvent. That's what it looks like. It's just a standard organic liquid, and one of the key things about it is it is pretty much environmentally benign. So one of the key things is we've been trying to move away from solvents that have hazards associated with them to ones that essentially don't are not hazardous, and also are very easy to prepare. So when Douglas was developing this, I told him you can have one synthetic step. Doug's a synthetic chemist. He likes to do lots of multi-step syntheses, but I told him he could do one reaction, and that's what he did to actually come up with this solvent. So just to remind you, here we are again with our process diagram. It's very similar for Sea Capture technology compared with MEA. We have our power station here with our flue gas coming in the bottom of the absorber. The solvent rains down, and then in the stripper you heat it up. That then goes to a compressor where the CO2 can be pressurized and then go off for storage. And the key thing here is this heat, which is the parasitic load, which usually comes from your power station, or maybe even a separate power station in some cases. So we'll talk about this heat in a second. One of the key things is this technology is just about CO2. Whatever else is in the flue gas doesn't really matter. So it doesn't matter whether it comes from cement works or from a power station burning coal or natural gas or an iron and steel works or anything like that. It's the reaction with CO2 that's key. So it's applicable to a very wide variety of gas streams. And I mentioned the energy penalty because it's very, very important. So for MEA, this is the energy penalty here, 30% MEA. And this is usually measured in gigajoules of energy per ton of CO2 captured. So for MEA, it's around 3.7 gigajoules per ton. It does vary very much depending on the nature of the engineering around the solvent capture process. But it's around 3.7. Over the last 20 years or so, people have been looking at what we call amine blends, where you have mixtures of amines, usually two, one of which gives a fast kinetics, the other one which gives a high loading, and that gives you around 2.7, 2.8 gigajoules per ton, something like that. And because our chemistry is so different, it allows us to really get step change in the steam use. So we're on about sort of 1.8, 1.9, something like that. So very different chemistry. So the parasitic load is actually much lower. And that really, really makes a huge difference to the economics of the whole carbon capture process, because that energy use is the main operating expenditure or OPEX issue with regard to the whole CCS process. So other benefits: low degradation, low corrosivity, minimal environmental impact. So corrosion, for example, is much lower compared with MEA. And if you can imagine, carboxylates are already quite oxidized. So when they come into contact with oxygen, they don't really do very much, certainly nothing compared with amines. So that actually makes them very low degradation rates. And for example, here, I've shown a graph of rate of CO2 capture with CO2 loading. So basically, when we've got fresh CO2 solvent here, which is this line, this dark line, what happens is over a period of time, as it's exposed to more and more CO2, the rate slows down as the solvent becomes more and more loaded. And basically, when you use an aged sample, so in this case, this is the sample that's been used for 6 weeks on a flue gas exposure action interaction, you can see the actual rate is a little bit higher, if anything, probably within experimental error. But the key thing is there is no significant degradation there in the rate of the reaction. And that's very, very important, because it means your solvent will last a long, long time. You don't have to spend a lot of money putting new solvent into your absorber. And you know, these absorbers are huge. You're not just putting a few kilos in, you're putting tons in. it's a very large piece of equipment. Okay, so how do we scale all of this up? So, Mohammed has seen our labs. Typically, we would do the initial scale up on perhaps a gram or maybe 10 grams of CO2 to start off with. And that's the sort of thing in a fume hood. This is what we call a vapor liquid equilibrium apparatus. And you can actually use this to work out just how soluble CO2 is in your solvent at different temperatures. And that's the key, of course, for our capture process. You want it to be very soluble at low temperatures, not very soluble at high temperatures, so it comes off when you heat it up. So vapor liquid equilibrium, very, very important for this kind of approach. You then transfer it onto what we call a pre-pilot demonstration, where you typically be working with a kilogram of CO2 per hour. Remember, CO2 is a gas, so a kilogram is actually quite a large amount of gas, and this is a demonstration rig that we had a little while ago when we were working through the scales. And now what we're on is a full pilot demonstration. So essentially between 100 and a ton of CO2 per day. And what we're now doing is moving to what we call pre-commercial demonstration, where we're doing hundreds to 1,000 tons per day. And for example, at Drax, the kind of scales there, you would be capturing 10,000 tons of CO2 every day. That's a very large amount of CO2, and it's a very large piece of engineering to do that. So I'll show you more details on this scale now. So this is one of our demonstrators at Drax Power Station. So Drax is one of the large, well, is the largest power station in the UK. And here is our demonstrating rig in a container. There's actually another container behind it, and these are our absorber columns here, where the CO2 and the capture agent are contacted. One of the reasons I like this picture here is because this thing at the back here, this is the ducting for one of the boilers, the flue gas from one of the boilers at Drax. Okay, so you can see here our whole equipment could actually fit inside the flue gas ducting there. And at the back of here, the back of our capture agent, there is an inlet, and the inlet here is about 10 centimeters diameter. So this I hope illustrates some of the challenges we face. We're going from something that has an inlet of about 10 centimeters to something that's got an inlet of, I don't know, maybe 10 meters diameter here. So 10 centimeters, 10 meters. It's a very, very large scale-up process. And this is just one of the boilers. They have 6 or maybe 7, actually, I think, at Drax at the moment. So just a few points on this project. Drax is the largest power station in the UK, generates about 4 gigawatts, which is roughly 7% of the UK supply. And 4 of their 6 generation units use renewable biomass fuel. That's very important, as you'll see in a second. So we've been working on about a 1 ton CO2 per day demonstration. And at the moment, the CO2 is vented into the atmosphere. But for our technology, we're working now towards larger scale trials, up to, say, 100 tons a day over the next 1 or 2 years. And then we'll have enough data, hopefully, to actually be able to build a very large plant. So Drax aim to capture up to 10 million tons of CO2 per year on scale up. And really, this is vital for meeting the UK CO2 emissions targets. And these are negative emissions required in 3 of the 4 IPCC scenarios to meet 1.5 degrees. So the key thing here is this is the potential for negative emissions. And I'll explain what that means and why we think there is potential there. It's when you're using biomass with CCS on scale. So this is a picture of Drax. So the sea capture plant is just in the middle there. You can't really see it, but these domes here is where they keep the biomass. So they import a lot of it from the US, although in the longer term, we hope a lot more will come from the UK. But they import a lot from the United States, southern US. And you can see Drax was originally on a coal mine. So they still use coal from time to time. So this is coal here. But that is essentially becoming not used anymore because of the issues around coal and the emissions associated with coal. So the UK is phasing out all coal derived power generation over the next year or so, and so that will disappear essentially. And so it uses biomass, which of course is potentially a renewable fuel. And this allows you to think about what we call negative emissions through BECCS. So what we've been doing for the last 100 years or so is we've been taking carbon out of the ground, and that can be coal, it can be gas, it can be oil, whatever. We've been taking it out of the ground, we're burning it either in a power station or in our cars or wherever. And as we burn it, of course, we produce CO2. So the carbon in the ground is being transferred into the atmosphere. BECCS is a potential opportunity to actually do the opposite of that, where you have CO2 in the atmosphere. And of course, with photosynthesis, with sunlight, that CO2 is converted into biomass, into trees. If you then harvest those trees, and the good wood you would actually use for construction or other applications, but the residual stuff that's no use to anybody, the twigs and the offcuts and the sawdust, you can actually put into wood chip pellets, and you can actually burn that, generate electricity. And if you capture the CO2, then it goes and put it underground. Then you can see you've got a mechanism there where the CO2 is transferred from the atmosphere underground. Okay, and that's negative emissions, negative CO2. So by doing this effectively, you should be reducing the amount of CO2 in the atmosphere. Now, you have to be really careful with this because there are embedded CO2 emissions in everything. So CO2 transport, biomass transport, chopping down your trees, running your power station, they all have CO2 emissions associated with them. So you have to be careful that you include all of those in your calculations. But even so, when you do that, you can still get negative emissions through BECCS. So just finally, to give you a few examples of real world projects where this is actually happening on scale. This is a power station in the US, in Houston, Texas, that I was fortunate to visit a few years ago, the Petronova plant, which is a coal-fired power station. and these are the various gas boiler ducts here. And basically what they have is some technology here, which is by Mitsubishi Heavy Industry, MHI, where they have an amine solvent technology. And hopefully now you understand what these things are. This is actually the absorber column. And so the amine solvent actually rains down this absorber column here. The flue gas comes up from the bottom. And then at the bottom, it's transferred into the stripper unit. And this is the stripper unit. So the stripper units are usually pressurized, and they're much smaller than the absorbers here, and much shinier because they're at higher temperature. They actually have to be made of a much more resistant material than the absorbers. And then basically the CO2 comes out the top of this pipe here. You can see just the pipe there. That's where the CO2 comes out of. And basically then it goes underground. And actually in this particular case, it goes to an oil field about 80 miles away, where it is buried and used for an enhanced oil recovery. Very much depends on the economics of the oil industry. This has actually been stopped for now because the value of the oil is not high enough to make it worthwhile. But it certainly helped MHI develop their technology and show that it worked. This is another example. This is a Boundary Dam in Canada, again using amine-based chemistry. I should say the Petronova plant captured just over 1 million tons of CO2 every year, and Boundary Dam here does the same thing, roughly the same scale, so 1 million tons of CO2. So pretty substantial amounts of CO2, and it's important to understand that these programs here, these capture plants, although they are capturing CO2, the main reason that they are built, the main reason they operate, is really to demonstrate the technology. When you're doing engineering on this scale, you can't just build something. You have to do it, scale it up gradually, and show at each stage of the scale up that things work. And that's essentially what they've been doing here. And just to show you, that's actually a part of the solvent tank. It's a huge vessel there, and that would typically be full of an amine. Okay, so it's very large volumes of chemicals that are being used in these kinds of processes. Okay, just to finish, basically what we've got is lots of different areas of industry where carbon capture can actually be deployed. Won't necessarily be in all of these, and there are options. For example, using hydrogen is very, very important for a lot of applications, but carbon capture also is competitive in those sorts of things. So it is steel, it is BECCS, so the negative emissions, glass manufacture, where you any highly energetic process, natural gas upgrading, so refineries, for example, cement, hydrogen, particularly manufacturing hydrogen from methane, so usually by autothermal reforming or steam methane reforming, shipping, oil refineries, waste to energy, and biogas that comes from anaerobic digestion of waste. So roughly, in this case, 37 billion tons of CO2 emitted per annum. 5,200 plants emit over 1 million tons of CO2 per year. And there's around 2,000 CCS plants need to be operational by 2040 if we're going to be net zero by 2050. So this is a very, very ambitious rollout of this technology, very, very challenging, but also, of course, we really need to do it because we all see what's happening in the moment around the world, and that's only going to get worse if we don't start to do things to tackle it. So just finally, how do we get there? So we need to fundamentally reduce global emissions wherever possible. Renewables, very, very important, but CCS is a key part of the transition. We've got all these industries we want to decarbonize. Negative emissions technologies are going to be very important. So BECCS is going to be very, very important. And we like to think that the sea capture technology is well placed to make an important contribution. And it's actually quite humbling to think that actually a lot of what we do now actually was first done in my little lab, the lab Mohammed worked in at one stage, and it's really sort of starting to take off now. So Sea Capture now is a fully fledged company. It has over 30 employees, sort of multi-million pound turnover every year. Still based in Leeds, but we do have demonstrators in other locations around the UK at the moment, and of course we hope to deploy them overseas as well at some stage in the future. So I'll just finish there, just introduce you to a few key people here. This is Doug Barnes, who's the head of chemistry. So Doug was a PhD student with me. And the other key person here is Casper Schulman, who's director of engineering and chief operating officer these days. So for many years, Doug and Casper were the company. Doug was a chemist, Casper was the engineer, and they worked together very, very closely through the years. Our CEO these days is Tom White, this chap here, and he's now leading the company. I'm sort of still a director of the company, but I certainly don't lead the day-to-day activities. That is Tom there. The various other people, James Wheatley, I mentioned some of his work. He now works for the company. That's him there, and Fatima you saw earlier, and Lucy is a Leeds graduate. So a lot of the people from Leeds University do end up in the company. We are fortunate that we've had some very generous sponsors. So IP Group, for example, are a venture capital group in the UK who have supported us from the beginning, pretty much. But Drax, for example, and BP are now full investors in the company. So they have seats on the board, all that sort of stuff, and then they contribute very much in terms of helping us develop the technology, providing access to demonstration sites, that sort of thing. And the UK government has also been very, very supportive. The Department of Business, Energy and Industrial Strategy given us a lot of funding, particularly early on as the company has evolved when we've been scaling up the technology. This is very, very expensive things to do. You can't just do it on a few £100,000 or whatever. It is a multi-million pound activity, and BASE and the government have been very supportive of us. So I think that is everything. Yeah. So thank you very much again, Mohammed and Dr. Mulyani for the opportunity to speak to you today. I'm very happy to take questions. I hope you understood what I said and I didn't speak too fast, but very happy to take any questions. Thank you for your kind attention.
Thank you very much, Professor Chris Traynor, for the nice presentation. I think it's clear, and then
probably
what's wrong, Chris?
Stop sharing there.
Okay.
Yeah. Okay, Mohammed.
Yeah, that's fine. So for the participants who have the questions to Professor Chris Traynor, can raise hand to ask directly and interact with Professor Chris Traynor. we have one participant, Pak Wirawan, please.
Thank you very much, Grace, for inspiring presentation and some contra-intuitive facts that you demonstrated, like adding acetic acid and organic solvent that can increase the pK. I think it's one of interesting fact you showed. But I was wondering from engineering perspective that you mentioned before, you are using like kind of bevel column in the adsorptions, if I presume correctly. Is there any a new development in terms of the absorption technology to increase the yield of CO2 absorption? Of course, we cannot beat the Henry's constant, we cannot beat the thermodynamics, but at this from kinetic point of view, we can still engineer stuff like, because I saw from your presentation that you use like a water column and then CO2 running from the bottom to up. And is it possible to use, like, for example, pack column that you might use lower amount of amine solutions to scrap the carbon dioxides? And this is my first question. And my second question will be, if you store the carbon dioxide into the grounds, how long that we can still do this storing? I mean, it's pretty much local. I don't know how much the volume that can accommodate the CO2 coming out from the from the plants. But is there any saturation point that we can reach if we keep pumping our CO2 into the ground? I think that's all my question.
Yeah, that's cool. Some good questions there. Yeah. So I can't say exactly what type of absorbers we use. Yeah. But so for example, for amines, people do use pack columns, you know, with glass or rashid rings or whatever. That's very, very common. Yeah. There's a picture actually that I didn't show where we have an absorber that was a tray column. You know, that there are all sorts of different absorbers you can use, and we've been working on optimizing that quite carefully. But I can't say exactly what we would use. But you know, you're exactly right. The sort of the interface between the gas and the liquid and maximizing that mass transfer and things like that is key. Yeah, we are slightly complicated because, you know, we have a slightly different kind of liquid. So MEA, for example, in water is very, very polar. You know, as perhaps tends to be a little bit more organic. So the way it clings to the surface of the pack column and things like that is actually quite different. So there is different behavior there. Yeah, but you're right. But unfortunately, I can't tell you exactly what we use. But we've spent a lot of time looking at pack columns. We've spent a lot of time looking at, you know, all sorts of different columns. So but it is a very important thing. And for amines, they do use pack columns. So that's relatively well established. With regard to storage and things like that, so volumes is not a problem. So there are lots and lots of holes in the ground that we can use where the CO2 can go. They're not always in the right place. That's one of the key things. You know, they're not always where you want them, right next to where there are a lot of CO2 emissions. So, you know, that there are issues there with storage of the transportation of the CO2 from where you capture it to where it's going to be stored. So, you know, certainly in the UK, there are going to be some large pipelines running up and down the east coast of the English and Scottish coast to actually go offshore, then to go for storage. I think in China, for example, they are quite limited in some of the areas that they have when they can do CCS, where they can do the storage. But actually, you know, the geologists have been working on this, and I think we have enough storage for hundreds, if not 1,000 years, in terms of the capacity that we can potentially use. So I don't think capacity is an issue. It's not always in the right place, but actually there's a lot of work being done at the moment, particularly in Norway, where they are looking to take other people's CO2 with ships. So there's talk of shipping terminals where you, instead of loading your ships up with natural gas, you will load them up with CO2, take it to a CO2 transfer station, and then it will be buried under the ground for storage. And I should say, Norway have been doing this for a long time. And Norway have been storing CO2, separating CO2 from natural gas and storing it underground in the Sleipner field for the last 20 or 30 years. Yeah. So they're pretty much ahead of the curve on a lot of this. They know what they're doing. And at the moment they are taking other people's CO2. But I think, you know, over the next 5 to 10 years, the volumes of CO2 that we're going to be producing either via CCS or other ways is going to increase exponentially. It has to, yeah. And so, you know, there are going to be other storage facilities that are going to be required. And I think one of the key things with this net zero transition is it's going to be quite a challenge, you know, managing the change. You know, you're going from a very much a hydrocarbon-based economy to one that's going to be based on, say, maybe electricity or certainly renewables or hydrogen, for example. It's a very big transition, and you have to manage it so that, you know, the standards of living for the vast majority of people doesn't change significantly. But you could imagine if we suddenly said, okay, no fossil fuels tomorrow, it would be absolute chaos. Yeah. But it's a more managed transition where fossil fuels are going to decrease gradually and renewables are going to increase significantly. So, and it's that balance and trying to keep everything as good as you can, but ensuring the transition happens as quickly as you possibly can. I think the other thing with storage that's worth mentioning, you know, there are various other ways with which you can take CO2 out of the atmosphere. So there's a lot of interest, for example, in planting trees, you know, because when you grow trees, they take CO2 out of the atmosphere. And of course, that helps with sort of negative emissions. But I think the other side of that, there has been a report very recently where, you know, all these forest fires we're seeing, you know, that CO2 that you've captured is not permanent necessarily. You know, it is very vulnerable to fires. And if we're not careful, particularly with a climate that's getting hotter and hotter, then the chances of forest fires is going to increase. And so actually, you know, relying too much on afforestation is dangerous. We need to do these other technologies as well, because they are very, very important. And, you know, essentially for CO2 captured underground, in principle, it should stay there along geological timeframes, and that's thousands of years, you know, whereas the lifetime of a tree, for example, might be 70 years, maybe 100 if you're really lucky. Yeah, but geological timeframes, if the CO2 is stored and stuck in a geological feature, it should stay there for thousands of years. So it is much more permanent storage, and that permanence is very, very important, and it's unique really to carbon capture. So I hope that answers your question. Maybe I didn't tell you as much detail as you would have liked, but I do apologize for that. But that's
no problem. Completely fine.
Thank you, Dr. Cipto Nugroho, for the question, and Chris for the answer. In the field of carbon capture, is there anything that we still need to improve or something like that, Chris?
I think the bottom line is, at the moment, we can do carbon capture, but the actual number of plants where it's done on the large scale and that whole infrastructure is in place is quite limited. So, you know, you need your industrial manufacturers, you need your capture plants, you then need transportation to storage, you then need the injection wells where the storage of the CO2 is stored. All of that in place on a very large scale at lots of different locations around the world. That's the key thing. It's rolling it out on scale all around the world, because, you know, even Drax captures 10 million tons. That's great, but on the worldwide scale, it's still very, very small. And we need to have thousands of these plants around the world to be able to really make a difference for climate change. So it's the scale of everything now, and the pace as well, of course. Yeah. I think in principle we can do this now, but we need to do it fast. And the other aspect, of course, is, you know, these plants are very expensive. So it's probably between £500 million and £1 billion for a large scale CO2 capture plant, such as the sort of thing you might put on Drax. I don't know quite what that is in your local currency, but it's a lot of money.
20,000.
120,000.
20,000. 1 pound.
20,000.
20,000. Yeah, Indonesian rupiahs.
Okay, my mental arithmetic
It's quite
isn't good enough
expensive.
to work that out, but you know, it's a lot of money for each one, and so you know, you need it's not just as scientists and engineers building these things. We need the investors, we need governments to actually back all of these things to actually get that sort of level of expenditure to be made, so that we can do this on the scale that we need to, and certainly the UK is starting to do that sort of thing. What it's doing at the moment is putting together what we call clusters. So in the northeast of the UK, we have a particular region where a lot of our manufacturing is done, and so that is a particular cluster. And what they're going to do is all those manufacturers are going to sort of join together, if you like, and have one CO2 pipe that's going to come from all of them that will go off for storage. So you have one cluster there. There's another cluster the other side of the country. There's one in the south. You know, so having these clusters where you have that major industrial activity is going to be very important. And the UK has been doing that. The US has started to do that too. But it makes sense. You know, if you have areas where most of the CO2 is produced, then that's where you start focusing on to actually start to get the maximum impact right at the beginning. And you know, some of these other things will start. Some of the smaller emitters will start to come in later on. But you know, big power station like Drax, you know, that's a key project to get off the ground.
Thank you. Okay, we have one participant who will be asking a question. Dr. Nurma, please.
Yes, thank you very much, Dr. Waton. Yes, good afternoon, Professor Renner. Nice to meet you here in IC3E, UNS. Yes.
Nice to meet you too.
When Dr. Cipto Nugroho has a question regarding the engineering part, now I'm asking in the field of environmental education, because I'm part of them. Yes, and then I joined the workshop related to the STEM education, and the issue that come is CCS, carbon capture storage, that presented by ExxonMobil at that time 1 year ago, and then this time to raise the issue of the sustainability and then climate change and something like that. I would like to hear your comment, your idea, because there is one statement that because carbon storage and capture and storage is expensive, and then it needs more energy, this is not a viable climate change solution. So there is one statement that I read there, and based on your experience, and also based on your, of course, your research in the geological effect that also asked by Dr. Cipto Nugroho, in the geological effect, it should be there is an effect in subsoil, and then it will change the water supply and something like that. I mean that, do you think that it is still should be one of the things, solution to reduce the climate change in terms of sustainability, if we want to have the STEM project to the student in the high school? Yes, that's my question. Thank you.
So hopefully I understood your question. One of the things I perhaps didn't illustrate properly with the storage is the actual storage happens about 1 to 2 kilometers down. So it's not just a little bit below the surface. Yeah. It is right down, you know, certainly over 1 kilometer down into the bedrock. So, you know, that's a long way down. And so it will stay there. It's essentially where, you know, natural gas has evolved over millions of years. It's the same kind of rock, so it should stay there. And so I don't think necessarily, you know, the sort of surface of the ground or whatever will be significantly affected. Yeah. In the UK, of course, we're looking a lot at offshore storage, and you know, and also in the US they're looking at onshore. And I think as these storage sites evolve, there'll be a lot of monitoring as to the CO2 levels around those storage sites, just to make sure that there isn't any significant leakage. I think that's very, very important. One of the key issues, and it comes down to environment and things like that, is of course CO2 is heavier than air. And so if you do have a leak, you have to be very, very careful. You don't want high levels of CO2 accumulating in a valley, for example, and things like that. And so people are looking at that quite carefully, making sure, particularly when it's onshore, that there isn't an opportunity for high levels of CO2 to build up. Geologists, I'm not a geologist, but they are looking at that very carefully, and these are very, very important questions that need to be looked at. In terms of the other work, your first question, I'll try not to be too political here, but I don't think I really listen too much about what Exxon says about CCS. Yeah, Exxon historically,
I know.
Exxon historically have not been the strongest in terms of supporting climate change and things like that. And there have been various documentaries in the UK just recently about ExxonMobil and they're sort of undermining the whole climate change agenda and things. So I'm very skeptical about anything they really say, to be honest. Is it expensive? Well, it certainly costs. I think that's certainly true. One of the problems we have as a global community, of course, is that whenever we've made something, built something, used fossil fuels or whatever, the actual price, the actual cost of the CO2 emissions and the impact it has never really been taken into account. We don't, it's not costed into the price of raw materials or anything like that. And things will have to change a little bit there, I think. Yeah. So although it is, I wouldn't say expensive, but it does cost significant amounts of money, and there's a lot of investment. But don't forget, over the next 30 or 40 years, people are beginning to be building sort of power stations. They're going to be building all sorts of things. These large infrastructure projects, they do cost a lot of money. Yeah, but you need to make sure that you're getting value for money, and you're spending the money on doing things in the most efficient way you can. Now, CCS is not the best for everything, and certainly that's very true. And there's a lot of interest in hydrogen, for example, at the moment, particularly if you can get hydrogen by electrolysis, so green hydrogen. You have to be a little careful, when you're making green hydrogen, that electricity that you're using doesn't come from a coal-fired power station, because that's not going to work. If it comes from a windmill or wind farm, then yeah, that's okay. But again, you have to be careful there that energy that you're taking from that wind farm is not meaning that you're having to run a coal-fired power station for longer than you would normally want to. So that balance between where you get your electricity from is very, very important. And shutting down as many coal-fired power stations as we can is very, very important. Moving to a hydrogen economy, I think that's going to happen. Whether you get the hydrogen from electrolysis, you will do. I think in the longer term, maybe 50, 100 years, all our hydrogen will come from electrolysis, and that will be absolutely fine. We'll get a lot of energy from there. But over the next 20, 30, 40 years, that's going to be much more difficult, and we are going to have to use probably fossil fuels for generating hydrogen. So, as I mentioned, steam methane reforming or autothermal reforming with carbon capture. So where you convert methane to hydrogen, and when you do that, you capture the CO2 at the same time, and then that CO2 goes off to storage when you generate the hydrogen. There are issues there. Again, you have to make sure that you don't get significant methane leakages. Historically, the oil industry has not been very good at preventing methane leakage. They are getting much better, and they know that there are some issues there, but they've still got some work to do, I think. But if they are going to be using methane for hydrogen generation, they've got to make sure that the leakages of methane are pretty insignificant. That's almost as important as actually producing the hydrogen there, because methane does have a much more significant effect on the environment than the CO2 does. There are a lot of petrochemical companies involved in this area. Yeah, obviously we work with BP, but Shell are very involved, Total, you know, all of the big petrochemical companies are involved. And there are a lot of environmentalists who actually automatically dismiss anything that has any vague interaction with the petrochemical industry. Yeah, I'm certainly not in that crowd, if you like, that group. I think, you know, the challenges that we face are so big that we can't exclude that part of the community. You know, all those engineers, all those scientists that work for the petrochemical companies, who you know, like they're individuals like us that live on Earth. They realize they can see the what's going on, and they want to do their bit too. And to actually say because they work for a petrochemical company, their inputs are not required or not valid, I think is folly. Yeah. But you know, having said all of that, you know, they're all always extremes, and I think, you know, there are some petrochemical companies that we can listen to. There are some that we should be quite skeptical about.
Yeah, we not listen to, but the workshop on the social responsibility. That's why the grant, everything, and then to how to train the engineer from the beginning, from the elementary school until how they can survive the environment, contrary with what the oil companies doing now. Thank you, Professor.
And they can see, they can see that their business, you know, in 30 years, they don't have a business. They, you know, so that, you know, the ones that recognize that and start to change now. And then, you know, they are getting a lot of pressure from shareholders, for example. I know Shell and BP get huge pressure from their shareholders and their annual general meetings to actually, you know, think about what's going on going forward, because, you know, their shares are going to be worthless if they don't change. Yeah.
Yep. Thank you, bro.
Okay.
Thank you very much. We have one more question. Okay, Dr. Cipto Nugroho, please.
You are still muted.
You're still mute.
Thank you that I'm still allowed to raise questions. I was wondering, it's going to be a very short questions. How about the feasibility of using adsorption technology instead of absorption technology? For example, you're using a liquid, but how about using the adsorption, like maybe carbons, activated carbons to absorb CO2? And I recently read that who is in Berkeley that's using MOF. They claim that they can capture CO2. They create a metal organic framework to catch like with a high adsorption capability. So how feasible is in comparison to the existing, I would say, the adsorption technology? That's all my question. Thank you.
It's a very good question, and there are companies out there that do that. There are lots of people. Well, there's lots of academics working in MOFs, but there are some companies as well that work on that. There's a company in Canada that I'm trying to remember the name of, but I can't. Savant, I think they are. Yeah, where they're looking at a lot of this kind of thing. With all technologies, they all have their pros and cons. Yeah, and a lot of it depends very much on the nature of the flue gas. Yeah. So adsorption, of course, is much more of a physical process. So you don't necessarily get the selectivity that you might get with a liquid-based process, where you know you're actually forming real covalent bonds, chemical reactions. MOFs historically have been quite expensive. You know, one of the key things is if you're building a capture plant, you've seen the size of the one at Petronova. If you're going to fill that with a MOF, that's a lot of MOF, and they can be very expensive. I know they're working really hard to bring the price down, and of course, whenever you talk to all of these people, oh yes, we can get it down to a pound, you know, the equivalent of $1 a kilo or something like that. Which maybe in 50 years' time, but you know, we're not there yet. Yeah. So you know, you have to take all of these things with a bit of a pinch of salt, but. I think one of the problems with the adsorption type based approaches is you do have to usually make sure things are dry. So most flue gases have got water in them. Yeah, so you need to take that water out. That's usually quite key. And also they are probably much more susceptible to impurities. than solution-based approaches. At least with a solution, you can actually clean it out. You know, you can filter it. There are all sorts of tricks you can use to get rid of any impurities. And one of the key things is most of these flue gases are not just mixtures of CO2 and nitrogen and oxygen. They've got all sorts of things in there. Yeah, okay, at low levels, but the key thing is if you're blowing this gas through it repeatedly over a very long period of time, then these although they're present in low levels, they will build up. And so, you know, for example, with coal, you get all sorts of impurities there. With biomass, you know, there's all sorts of, you know, you get high levels of potassium, you get particulates, all sorts of things. So it really varies quite considerably. And for a lot of separations, they work perfectly well, beautifully well, if you've just got CO2 and nitrogen, or CO2 and oxygen, and nothing else. And it's always those other things that really make a difference into how adaptable a particular technology is. And I'm sure that, you know, there will be applications where you can use adsorption. And you know, that's to say there is that company in Canada that's commercializing a lot of that sort of thing. So yeah, it is possible. I think the other thing, you know, goes back to what I was saying about scaling everything up. At the moment, we just don't know all the economics, you know, and the economics when you make say a small reactor, or, you know, maybe something that works on 100 tons or 1,000 tons of CO2, the economics are important, but actually not too much. But then if you want to make 1,000 units, each one is going to capture 1 million tons of CO2, you know, the economics then, and you know, availability of resources and all those sorts of things suddenly kick in. So, you know, I can imagine a lot of the solvent manufacturers now are rubbing their hands thinking this is going to be a gold mine for them, because it probably is, yeah. But, you know, all of those sorts of things are going to have to be scaled as well. And at the moment, I think we did a calculation a while ago that to fill Boundary Dam with MEA probably used, you know, almost the equivalent of the world supply of MEA for that one particular year. You know, it's not quite as bad as that, but you know, it's that sort of area of calculations that you're having to do. And then if you're going to build 1,000 of them, you know, you're going to have to be making an awful lot of amine, or an awful lot of MOF, or an awful lot of activated charcoal, or whatever. So, you know, it's the challenge of rolling this out on scale that really is bewildering, really. It's you know, but it's the sort of thing we've got to do. And you know, one thing I will say is that there's lots of technologies out there, and over the last 5 or 10 years, I've seen lots of academics and companies sprout up, everybody having the best technology that's going to save the planet. Yeah, which is great. And you know, we're just the same as anybody else. Although I like to think we got in quite a lot earlier than many people. But it's only when you run these things for a prolonged period of time in the real world that you really see how good they are. And there will be some technologies that survive. There will be quite a lot, I think, that will fall by the wayside. And it's very hard to predict which ones, you know, what's going to happen to each one until you roll them out and you have them running for a year or two. And then, you know, after it's running for a year or two, then you really see what the effect of impurities is, you know, how much you have to spend either putting more solvent in or refreshing your MOFs or whatever it is, you know. And that's the sort of thing we're at the moment. We don't really know all of those or variables, or maybe we do, or companies do, but they're not going to tell anybody about it. Yeah. Because they think, oh, well, we can improve that, and in 5 years' time, that won't be an issue. Maybe not. I don't know. Yeah. I mean, the other thing that of course, that's happening a lot at the moment, very popular, is direct air capture, where you actually have an absorbent. It could be potassium hydroxide, but there are lots of others as well, where you just have a plant that draws air through it and takes the CO2 out of that air. Now, the problem there is, of course, you've only got 400 ppm. We say there's too much CO2 in air, but actually to take 400 ppm of CO2 out of air is a real challenge. You can do it, but it's very expensive. And you know, it's probably about $500 to $1,000 per ton of CO2. But there is a company project in Iceland where they're doing this, but it still is on a relatively small scale, and it's the sort of thing that, when everything is decarbonized, in 50 years time, when everything's decarbonized, these sort of things perhaps might make a difference in the grand scheme of things, just keeping the balance, but actually to withdraw enough CO2 to actually make a difference to climate change, I don't think it's going to happen. It's just too energy intensive and just too resource intensive as well for the amount of CO2 it would actually take out. And at the moment, we really need to focus on point sources where you've got 10%, 20% CO2 coming out the chimney. There's no point in trying to fiddle around separating 400 ppm until you've sorted out all these other things, because they just blow the 400 ppm out of the water in terms of the volumes and amounts of CO2 you can capture by.
Yeah, maybe we need to plant more trees to catch
Plant more trees.
more dispersed CO2. Otherwise, it's a difficult issue.
The right sort of trees in the right places. I think that's what we always say. Yeah, because what's not to like? Yeah, it's planting trees. It's relatively easy to do. It's relatively cheap. We should stop chopping trees down unless we're going to use them for something viable, like construction. One of the nice things, for example, if we can use biomass trees for building houses and things like that, then that's infinitely better probably than using a lot of cement. There's huge embedded CO2 emissions in cement. We can use trees for construction materials, but there will be the offcuts that we can perhaps use for the BECCS as a fuel in a power station. We have to be careful that we don't try and do that on too large a scale, so that we're burning too much wood. We don't want to do that. It's very tempting just to rely on these negative emissions technologies and have them utilize them extensively to offset everything that we don't really want to decarbonize, but we really should. So that balance is very, very important going forward. And I hope certainly with the COP27 and various other things, people will become wise to that. And they'll put some proper guidelines in that'll actually manage that to transition carefully, such that people don't start abusing the system and doing the wrong things, usually for the right reasons, but the wrong things. Sometimes not always for the right reasons, but there you go. That's human nature, I'm afraid, to a degree. Yeah.
Thank you for your explanations.
Thank you.
I'm sorry, Chris. It's always nice to continue the discussion, but unfortunately, we have to end this session.
Okay, that's fine. It's been very nice to talk to you all, of course. Yeah.
Yeah. Before we end the session, we have the token of the appreciation for Chris. Here, the certificate of appreciation from the committee to Professor Chris Trainer. Hopefully, you are happy to receive this certificate.
Of course, thank you. Will it come through the post, Mohammed?
Sure, yeah.
Very good. All right, I'll put it on my wall in my office. Yeah.
I will print it and post it to you. Yeah. So from Professor Chris Trainer, we learned about the chemistry of carbon capture and also storage. Hopefully, the technology that has been applied in the UK can be also applied and adapted in Indonesia, as we know that we have the potential to also apply in the same technology. We have the natural resources, and also probably in the future our government can consider to give the funding to improve the quality of the research in carbon capture storage, or also can collaborate with the research institution or carbon captures in the future. Thank you very much, Prof. Chris Trainer, for sharing your knowledge and your works with us. See you in the next agenda. Thank you very much.
My pleasure. Thank you very much, everybody. Bye-bye.
Thank you, Chris. So the time, I will give it back to the Satria and Camilla.
Thank you from Prof. Rainer and Dr. Watton for the insightful presentation. And now, ladies and gentlemen, that's all the agenda of International Conference on Chemistry and Chemistry Education Day 1, 19 August 2022. And we as the master ceremony, we do apologize for the inconveniences during this event.
Thank you very much for your attention and cooperation. Tomorrow, we still have interesting presentation from our keynote speakers and also parallel session. So see you in IC3E Day 2.
Assalamualaikum warahmatullahi wabarakatuh.
Wassalamualaikum warahmatullahi wabarakatuh. Bye bye.
See you tomorrow.